So there are 6 geometry questions in this AMC 8 competition, including plane geometry, solid geometry, and coordinate geometry. We'll see these problems one by one. Question 2 is an easy question. So it talks about a big rectangle consists of 3 identical smaller rectangles. And also, the one side of this smaller rectangle is given. And for geometry question, it would be helpful that you write down all the conditions in the picture. So here what they see is there is 5 feet, which is the shorter side of each smaller rectangle. So this is 5, this is 5, and that is 5. Once we write down this 5, you can directly see that 5 plus 5 is 10. So what this 10 means, the 10 would be the length of the longer side of this rectangle. So for each smaller rectangle, the area would be 10 times 5, which is 50. And the question is asking what is the area of the big rectangle. Of course, it's just 50 times 3. And the answer should be 150. So we solve question 2 very quickly. Is a solid geometry question. It's regarding the volume of a cylinder, but it's also basically a straightforward question. Why? Because we know the formula for the volume of a cylinder. It would be pi r square h, where pi r square calculates the area of the base cylinder, and h is the height of that cylinder. The volume is base area times the height, pi r square h. Then here we have 2 different cylinders. The condition givings including height and the diameter. But from the diameter to the radius, that's easy. So just divide the diameter by half. You would get the radius. Then we can find the formulas for the volume of the 2 cylinders. So one is by Alex, the other is by Filica. So we want to know the volumes of these 2 cylinders. Of course, we have pi. For the first one, the radius is 6 diameter. The diameter is 6, so the radius is 3. So pi times 3 squared, then times the height, which is 12. For the next cylinder, we also have pi r squared, but this time 12 centimeters is diameter, so the radius is 6, so 6 squared, and then times 6. Okay, we need to find these 2 ratios. But to calculate things quicker, do not get the 2 products, because it won't be useful and it will only cost you time. So what the right thing to do is you simplify the ratio. So first, you have a pi here, you have a pi here, you can ignore. Second, here is a 3, that's 6. What is the ratio of 3 to 6? That is 1 to 2. So now you can change this 3 squared to 1 squared, and then here 6 squared to 2 squared. Next, here the height is 12 versus 6, which is 2 versus 1. So then times 2 times 1. Now things are easy to calculate. 2 over 4, which is 1 over 2. That question finished. 12 is again a solid geometry problem. It's related to the surfaces of a cube. So a cube has 6 surfaces, and they are colored by 6 different colors. And the question I ask you to find what is the opposite face of the aqua. If you look at the question, it looks difficult. Why? Because in the 3 views given for that cube, you do not see a single surface which is colored aqua. Then it looks difficult. But actually, if you see more clearly from these three views, three pictures, and you could get the answer fairly quick. If you look at the three pictures, you'll see which face appears most. It's actually the red face. So red face appears in each of the three pictures. So the right question to consider now should be, what is the opposite face for R, for the red face? Why we can solve this question? Because in all these three pictures, it shows many faces that are next to red, but not opposite to right. So in order to find this answer, we know there are many choices that are not possible. From the first picture, we know that both B and G cannot be the opposite face for R, because this picture shows that B share a common edge with R, G share a common edge with R. Similarly, for the second picture, what we can see, we know that WB, B is already included, so W also cannot be the opposite face of R. Then let's see what happens for the third picture. So the third picture has RPG, so we know both P and G is already included, so P cannot be the opposite face for R. So we have 6 different colors. 4 colors have been excluded to be the choice for the opposite face for R. Then what would be the only possible choice remaining? That would be the 6 colors, right? What is the 6 colors? That is aqua. So from that analysis, we know what would be the answer to this question. It would be R, red. Finished. Question 11. That is a coordinate geometry problem. That's probably the first time in the recent years that coordinate geometry appear in AMC 8. But as we know that MA already announced that starting from this year, there will be something like quadratic equation, coordinate geometry would possibly appear in the last 5 questions. And this coordinate geometry problem, actually, if you understand what is the meaning of all the notations, it's not hard. So for a coordinate plane, it just means you have 2 directions. The horizontal direction is called x-axis, and the vertical direction is called y-axis. And then you could have a grid. So here, to save some time, I already draw the coordinate plane on the board. And remember that in AMC 8, grade paper is allowed. So actually, if you have a grade paper in hand as your scratch paper, that would help you to solve coordinate geometry problem quicker. So here we have a coordinate plane, and then in the questions, 3 lines are given. The first line is called y equals 5. What does it mean? It means all the points with y coordinate 5. So, of course, if x equals 0, you would have y equals 5. 1, 2, 3, 4, 5. So this point should be in line y equals 5. So we know that in a plane, in order to determine a line, we only need 2 points. Then a line is determined. So we need another point in the line y equals 5. So x can be anything. What happens if x equals 1, y equals 1? Y equals 5. So that will be this point. So we can connect the lines. Clearly, y equals 5 is what? It's just a horizontal line. Right? Now we can apply the same techniques to draw the other lines, which in order to determine a line, we only need 2 points. Let x equals 0. Then in the line y equals 1 plus x, y would be 1. Let x equals 1, then 1 plus x is 2, so y is 2. So actually this would be the line for y equals x plus 1. From this, because actually x has coefficient 1, and you could also see from this picture, this is actually a 45-degree line. This is 45 degree, and that would be 45 degree as well. And now the third line, y equals 1 minus x. Again, we choose small numbers for x. If x equals 0, then y equals 1. So we have this point as well. If x equals 1, y equals 0, right? So it would be that one. Then we can draw a line which is kind of in that direction. And also it's kind of like 45 degree with both x and the y-axis. Then there's the triangle. The triangle is the one that's formed by these three lines. So here would be the triangle. So clearly you will see what is this triangle. This triangle just consists of two smaller triangles. And each smaller triangle is a right isosceles triangle with size what? 1, 2, 3, 4. Giving this is 45 degrees, that must be isosceles triangle, so this side must be also 4. Then what will be the area? Each small triangle here is 4 times 4 divided by 2. So for the combined one, this big triangle, it would be just 4 times 4. It's double of this smaller one, right? Which is 16. So that is question 21. Not hard. We see question 24. From the feedback I have received from parents and students, probably this question is the really difficult question in this competition. And I will show you two methods. The first method is the method I use to solve this question, which use a very powerful theorem. And then I will show you the second method, which is also a typical method dealing with the ratios and parallel lines in the triangles. And in this question, the conditions given are related to the ratios in certain triangles because there are some lines inside the triangle, so the ratios looks a little bit complicated. Now let's ignore the picture in the problem. We see what is the general situation. In order to construct a relatively complicated picture, the general situation would be you start with a triangle. Now here we have triangle ABC, which I write in black color. And then you consider another line. This line does not pass any of the vertices. Then what will happen for this line which relates to that triangle? It will intersect with each side of this triangle. It could be that this line just intersects with the interior of a side, or is actually intersect at a point which is at the extension of a side. So the three intersection points I will denote by D, E, F, where the original triangle is denoted by A, B, C. So this you will see as a typical structure, and of course the reason why I'm talking about this is actually you could see such typical structure in this question 24. So once we have this typical picture, what is this theorem talks about? This theorem actually links three ratios. And they claim that these three ratios multiplied together is 1. Let's see what are these three ratios. The first ratio says AF over FB. So this is the ratio formed by that intersection point. So that intersection point cuts this side into two parts. One is AF, the other is FB. And then we form a ratio, AF over BF. And then we go in kind of like in a counterclockwise direction. We consider the next edge, which is the next side, which is BC. And in BC, there's also an intersection point inside the side. So by forming similar things with AF to FB, what we have? We would have BD over DC, right? The intersection point cuts this side into two parts, BD and DC. So that is a Next ratio. What is the third one? The third one, of course, should be related to the side AC. But this side is a little bit complicated, given that the intersection point is outside the side AC. If we follow the same rule, which is you use that intersection point to form a ratio, so that would, the two line segment would be O from the intersection point to the two vertices. So that's why it would be EA and EC. But given that we have to write down the line segments in the counterclockwise way, so AF, FB, and then BD, and then DC, right? AF, BF, BD, and then DC. So that's the next one. In this ratio, it would be C. So the line segment here would be from C to the intersection point E, and then from A to that intersection point E. So that would be this general formula. And how can this general formula help us? Because in this picture, in our picture, we have something similar to that. So now I will draw the problem picture again. So here ABC is actually a big one. And then we have D, which we know what is the ratio, right? I use green color. So AD versus DC, that is 1, 2, 2, right? Next, we will have another line segment starting from D, which we have E is the middle point, and that point is named F. So what is the next ratio we have? The next ratio we have is BE equals ED. In other words, BE to ED is 1 to 1, right? So now let's see how can we use this Menilov theorem. And by using this theorem, we will see what are the two conditions we have. Actually, the two conditions we have are in which line? In this line, BD, and in the other line, which is AC. If we want these two lines to form a triangle, what is that triangle? This triangle would be just B, D, and C. So for that BDC, we can use Menilov theorem, and that will give other information about another ratio. Okay, let's apply this Menilov theorem. What do we have? If we're starting from D, we will have DE over EB, right? Vertices to the intersection point, then intersection point to the vertices. So next, it would be B vertices to the intersection point F, and then intersection point F to the next vertex C. And the next ratio would be a little bit tricky. It has to be, so maybe to make things clear, I draw the intersection point again. So we will have C to the intersection point A versus D to the interpoint A. That equals 1. So DE over EB, that's 1, we can ignore. So BF over FC times what is CA over DA? CA is the whole thing, DA is just this. So it would be 1 to 1 plus 2, so 1 to 3. So CA would be 3, DA would be 1, that equals 1. Then what is the condition we have? We will have, what is the result we have? We will have BF, we can get the ratio for BF over FC. That is what? That is 1 over 3. So that is a very important ratio we get from Menilov theorem, which will help us to calculate the area. Get the ratio of BF to to FC, because that ratio will be essential in calculating that area BEF. And that also can serve as a general method to solve this ratio problem. So here the situation, as we just analyzed, is the two given ratio conditions are on two different line segments. One is AC, AD over DC is 1 to 2. The other is BD, E is the midpoint, BE equals ED. So these two lines are not directly related to this line BC. So which means we need to figure out a method that somehow can translate these ratios from other lines to this bottom line. So what the Menilov theorem that I just mentioned is one way, because they link the ratios in three ratios in a triangle. So you know two ratios, you can get the third one. And another typical method is actually to use similar triangles. So here, the blue picture is a typical, it's a baby model. It's a typical picture. You'll have two parallel lines. Then what is the two ratios are the same, which is AD versus DB equals AE versus AEC. Or a similar one would be, we can write also as AD versus AB equals AE versus AC. So the idea is, once you have a parallel lines, whatever the ratio in one side, ADB, in this side, you form a corresponding ratios in the other line, AEC. The ratios would be the same. So you can then this formula gives us a way to translate the ratio from one line to the other through the parallel lines. So now here, in order to make this ratio coming down, so what shall we do? We need parallel lines. So that's why a typical auxiliary line in this type of geometry problems is you draw a line parallel to AF from D. So these two lines are parallel. Then what happens? BE equals ED. If we name this new point G, so we know this ratio would translate down to here. So BF versus FG is 1 to 1. Now next, we know that AD versus DC is what? 1 to 2. Now by these parallel lines, it can translate down. So 1 to 2, so 1 to 2. So FG to GC is 1 to 2. So now what we know, of course, BF to FC is 1 to 3. So that is a key fraction that can help us to solve the area later on. So let me write down this ratio, and then we continue to solve the area that the question is asking. Now we discuss the second part of this question, which is to really calculate the area of this small triangle BEF from the condition that the big triangle ABC has area 360. So before going into the detailed steps, let us review another formula related to the area of triangles. So this is a typical structure. If you have a triangle, you put a line inside the triangle to divide the big one into two small triangles. Then these two small triangles, ABD and ADC, they would share the same height, but they have different base, BD and DC respectively. If we want to know what is the ratio of the two areas, given that they have the common height, remember in the area formula of triangle is half times the base times the height, right? They have the same height. So when we talk about the ratio, we don't need to worry about the height. We don't need to worry about that half in both expressions. So we only need to worry about the base. So if you have two triangles that have the same height but different base, then their area ratio would be just the base length ratio. So that is a typical structure. Now we look at to see what are these typical structure in that question. So to make things easier, I will just ignore the S. I will just write down the area, the name of a triangle, and use that to denote the area. So triangle ABC has area 360. What can we know? We know, actually we can know that what would be the triangle ABD. Why is that? Because ABD versus BDC is 1 to 2, right? So ABD area versus area of BDC is 1 to 2. So what does it mean? That means you need to divide 360 by 3 portions, then each portion would be 120. So we can get the area of the two triangles, given that we care BEF, so maybe we only think about BDC for now. That would be 240, right? So we get that part, 240. What's next? Next, in this one, we know the ratio here, right? 1 to 1. So how about we draw this line? We're connecting CE, what we have. In triangle BDC, E is a midpoint. So the area of BEC and DEC would be the same. So the area of BEC would be 120. Now we get the area of a smaller triangle. So final step. The final step is to calculate the area of triangle BEF. So what is that ratio? The area of BEF to the area of EFC is 1 to 3. So we need to divide this 120 into 4 portions, and one portion would be BEF. So now we know the area of triangle BEF. It's just 120 divided by 1 plus 3 divided by 4, and the result is 30. So we find the answer to probably the most difficult question in this competition. Answer 30, we should choose B.